Good morning,
Morning.
Dr. Afeyan. It's so nice having you today here in London and to have an interview with you speaking about so many things that are a big concern or are really interesting in our lives. And most of them are connected to our life, our health, our well-being, our longevity, the longevity of our life, and so on and so forth. And of course, dear friends, it's not necessary at all for me to introduce Dr. Noubar Afeyan because of many factors. I think those who were in academia knew about him or knew him for many years when he was professor at MIT, when he was a researcher, founder of Flagship Ventures. Then he became world popular because of the pandemic, the founder, co-founder, and the chairman of Moderna that had saved millions of lives. For me also, Mr. Afeyan, if I would try to describe him in a couple of words, is a real traveler, researcher that doesn't travel to discover America from Europe or going the deserts of Central Asia to discover China, but he's traveling in the jungles or in the space of science to discover for all of us the new frontiers of science, especially the most important science that I do think is the science of life. We have done and we know a lot about elementary particles, the cosmos, but it looks like we don't know much about ourselves, our body. And maybe there is a reason, and this is one of the things that I would like to discover with Dr. Afeyan. But of course, Dr. Afeyan is someone, a visionary. I would say by his character, he's also a teacher because I've seen personally how much he's doing for educating young people and opening doors for them for their research in the future. He's also someone is doing huge amount of charity. He's someone also that he described himself. In fact, yesterday I was at the Royal Society, described himself as a migrant. Migrant in a very positive meaning of this word. Someone was born as an Armenian in Lebanon, then migrated or traveled to Canada, and then from Canada to the United States, eventually became one of the leading scientists and entrepreneurs of our times in biological sciences. Imagine that he would stay in Beirut, what he was doing that now today in Beirut. So migration has many aspects, but one of them is also connected with developing our societies. Because to be honest, all of us, we are migrants, and probably some 60, 70,000 years ago, we migrated from Africa. So migration is a good thing. And of course, Noubar is also someone that values humanity because he's one of the co-founders of a movement, I would say, called Aurora, together with Vartan Grigoryan, late Vartan Grigoryan, and Ruben Vartanian, basically valuing absolutely human behavior in your life. When you, in many cases, sacrifice your health, your time, everything that you do in order to support or help or rescue others. So from my description, I think we probably have to have another 10 hours of an interview, Noubar. But that's once for the time. So today we will concentrate, of course, and this interview is for our Advance Tomorrow Summit conference in Singapore, and I will focus on science and technology and biotechnologies. So again, welcome to the summit.
Great to be here. Thanks for the very kind introduction.
And let's start with a simple question, and probably I will ask you to do a very short answer to this. What do you think about health, life, well-being, and how its connection with politics? We cannot avoid geopolitics these days. The wars happening here and there. And what do you think? Is there a connection? How geopolitics impacts life?
Well, look, I think despite all the efforts we've made to improve human health, especially now coming out of the pandemic, we realize how vulnerable we are. And in fact, many of the decisions made during the pandemic as to how different countries dealt with it and how different countries did not help each other in dealing with it, were purely political and geopolitical decisions. And so it created a sense of vulnerability everywhere. But to be honest, having worked in healthcare for 36 years, what amazes me is the degree to which, as humans, we are fatalistic about our health. Since we are told from a young age that people around us will get sick and they will die, when it's our turn, it almost feels like we resign ourselves to this inevitability. On the other hand, you could imagine that we could have thought the same way about our physical security, that is, being alive, not for health reasons, but just our danger that we face. And there, people are extremely protective, and they demand that their government protect their physical health from terrorist attack, from war, etc. So I've always viewed a dichotomy about the fatalism that humans manifest in not really demanding from their governments what I call health security, but instead being satisfied with health care. And in fact, to me, health care is a complete euphemism. It really means sick care, because you only get it when you're sick. If it really was health care, you should get it when you're healthy. And that's the mindset we use when it comes to physical security. All the scanners at airports, all the secret police that are here and there trying to protect us, none of that exists in the medical field. You basically are on your own until you manifest disease, ideally really serious disease, ideally really late stage disease. And I say ideally because it's much easier to diagnose, and it's much easier to offer treatments to late stage disease because something will get better. Instead, what I envision in the future, and it really is all politics at the end of the day, is the will and the demand of the people, of the governed, to say, no, our government owes us health security. From the day we're born, we should be given every form of protection to preempt disease, that is to delay it, to deter it, to prevent it if possible, and at the earliest possible sign of onset of any kind of disease, early interventions, and then eventually, if all else fails, yeah, we can take some treatments. That's the opposite of what happens today. So I do think those are tough political, and we're sitting here in London. The UK has its own single payer kind of national universal healthcare coverage, but innate in that are political decisions. Many drugs that are approved elsewhere aren't reimbursed and available here because they've made a choice that the value of the treatments in terms of lives and the value they put on those lives isn't worth the cost that the supplier is providing. Again, in an environment where you resign yourself to the fact that you're going to get sick and may not get treatment for 2-3 months, whatever, I don't understand why people don't value their lives more. And I think if they did, governments would have to take a very different look at this.
Well, can we say that at the end of the day, whatever is happening to our health as well is very tightly connected with politics and specifically geopolitics? And can we also say that unfortunately geopolitics worldwide and politicians are representing national interests rather than global or human interests? Because if you are focusing on health issues more or less are the same in specific different countries. So it's a global issue rather than a national issue. While security issues or military issues or diplomatic issues are very national issues. Health is the one that is basically global. I think any solution found in China for specific pandemic or the United States covers the whole world. It's not a national, it doesn't work only for Chinese or for Americans.
So there's two things that make it national though. One is that somebody has to pay to do the research to find the drugs. And in this time, basically the United States pays the vast majority of the cost of finding and making drugs. And the reimbursement that they get in the US mostly covers the cost of this, which is increasingly a political issue of its own that is driving a massive national dialogue in the US. You've seen the most recent Inflation Reduction Act in the US, IRA. They put in provisions that made pretty draconian kind of cuts or at least mechanisms to limit the cost of medications, prescription medications. Those things, and we'll see how they pay out, but this is kind of the industry has viewed it as a pretty big limitation. At some point, somebody has to pay both to develop and discover the drug and the cost of the drug. That becomes national because it's American taxpayer money largely that is subsidizing this for the world. And that you can imagine the same is being said about military, right? I mean, for the longest time, the US has complained that it pays the bill for NATO disproportionately. In a way, these big issues blur because of the money part. You're right in that, so the flip side of this is that if it's an infectious disease, mostly, then because of the mobility in the world, as we saw, whether it's Wuhan, China, or Italy, where there was a big cluster of COVID-19 early days where people lost their lives, this is a global thing. So who pays to come up with solutions? In this case, the US government paid for most of it, and I mean, through our intervention and a couple of others. That should be made available to the world. So yes, solutions should be freely available. Who pays for it? It'll all come down to the issue of nationalism and therefore resources.
Yeah, but at the end of the day, of course, United States and other Western states, they pay, mostly for the moment. Other states as well pay, but there's also a time of payback, because if you're a US-based company and there is a drug that is a global drug, then you get paid mostly in the United States. So there is a balance. Mm-hmm. And you say US government pays for the development, but then it collects back as well in the form of taxes from the big parts of pharmaceutical companies.
In COVID, that was the case. Look, I think what I'm saying is, I think it's political, it's geopolitical, but the fact that we should think about health as a form of wealth and therefore worth protecting, worth growing, that's not a mindset that we're living with right now.
Yeah. Well, thank you very much. I think that's very clear, sort of an introduction from your side, of course, to the perspective of why on earth geopolitics is important for health. Mm-hmm. Now, it takes us sort of naturally to another question, which is how much in reality our health systems worldwide and nationwide are prepared for the next pandemics or next health problems that humanity is going to face. Are we resilient? Are the health systems that you observed, especially during the pandemic, are they resilient? What is necessary to be done to make healthcare or health prevention or disease prevention much more resilient?
So I would say, I mean, the simple answer is no. I don't think there's a lot of attention paid to resilience, because resilience is always kind of gathers momentum after there's been a failure, and until one forgets about the failure, resilience becomes still important. And then as soon as the failure is forgotten, then resilience goes out the window. This has happened before. If you remember, in decades ago, there was pandemic preparedness initiatives that cut across multiple U.S. administrations, and it was funded. And then that funding was pulled away because of some short-term convenience, and we didn't have enough money, etc. So what we saw during the pandemic is, on the one hand, good news, because in this case, it wasn't kind of such a fatal thing. Within a year, solutions were found and things were opened, and then we operated again. And I worry that's going to give people the wrong impression that therefore we must have been resilient empirically. On the other hand, I think it showed that the kind of the vulnerabilities we sensed every day and all the things that could have gone the other way is such that I wouldn't count on that again. It would be like, thinking you're going to throw, I mean, we probably threw dice and got the same number 10 times in a row to do what happened during the last pandemic. I don't think you want to go into the next one and say, I bet I can throw another 10. That's the way it feels to me. And the reason for that is that we have different ways of thinking about healthcare, but we should think about healthcare as, what are the tools available? Treatments, diagnostics, what do we do in prevention? And by the way, it's an interesting dichotomy, because healthcare in the preventative side is public health. Healthcare in the treatment side, once there is a pandemic, is actually medicine. And medicine and public health are quite different things. They're funded differently, they're practiced by different people, decision making is very different. So one has to also think about whose responsibility is resilience. Is it the health services responsibility, or is it some esoteric, public health obligation, which is usually underfunded by definition? It's hard in a weird way. I keep telling colleagues that if this was viewed as defense, right? Defense invests in preventing war, detecting war, surveillance, intervention, all sorts of things before war breaks out. Diplomacy, exactly. All of that is part of defense, and including defending the country using big weapons, etc. In health, we have no defense. We just basically wait till war, and then we deploy very, very expensive weapons, and it's almost too late. And even the responsibility of that is split as a result. So that's one thing I'd say could be fixed. The second is, if you think globally, healthcare delivery is quite impaired. I mean, we saw in low to middle income countries during the pandemic, even when vaccine was available to be shipped, a lot of that vaccine was basically wasted because they couldn't get it into arms. They had no healthcare infrastructure to reach remote regions all over the world, particularly in Africa. And while there was a lot of noise made, that was also quite political, of governments saying we demand that we get the vaccine, the reality is they had no way of getting it to their people, and they didn't. And it took a very long time to set up that infrastructure. The problem wasn't, in my view, vaccine availability, or certainly the main problem wasn't that. The problem was the inability to reach a vast number of people. So that, but whose problem is that, right? So the countries in which this happens may not have the means to do it. Some of the philanthropy groups are trying to help there, but this is an overwhelming problem. Is it the West's problem to solve this for other countries? So these are all things, just like climate change, that eclipse national boundaries, but people aren't really willing to do that much about it. I mean, they're willing to talk about it. So yeah, I think that, look, in the case of this pandemic, there was clearly, I will say we got lucky, because it so happened that this virus was amenable to an intervention that the company that I co-founded, Moderna, had developed the technology for 10 years to actually be able to counteract. Not with this in mind, but it so happened this was such a target. But there will be other threats that, for example, antibiotic resistance bacteria, we have this technology is not going to work for that, and we have no good solutions for that right now. So if there's a major bacterial outbreak through the food system, through in other means, that will be, we'd be really gambling that we could come up with something quickly. So a lot of work to do. Again, I think it starts from governments beginning to embrace this notion of health security as opposed to health care.
Yeah. I think, can we say that most probably we're facing two major issues. One of them, the one that you had just raised, about health security, because we're very used to speak about climate security, food security, water security, but we don't speak about health security. Right. And that's about a global approach, and it cannot be only national, it should be global approach. Again, where it's thinking or acting nationally in many cases rather than acting for the whole humanity. But health security is a key thing, and we have to start changing ourselves to moving from whatever we are doing to more and more to health security. But probably there's another issue that I'm thinking about it as a former physicist. The approach to how we are doing our research. If you take physics and mathematics, physics is a classical science in the sense that it's based on laws of nature, clear cut. There are formulations in many cases, even in quantum mechanics, you can end up with a mathematical formula. It's now when you get in statistical physics or statistical quantum mechanics or big objects, then I think formula that doesn't work in many cases, then you have to go to modeling and so on and so on. But basically, we always think that there should be a mathematical formula. So that formula is there, then a theoretician can predict something, and an experiment can catch up, say yes or no to the result of that prediction, and that helps the science to go. The way I see, I'm not a professional biologist, biology is mostly empiric. It's an experiment, rather than theory behind it, predicting what should be the next one. There is, but it's not on the scale of like we have in physics. So basically you have a lot of trials here and there. As you said, you are developing something that humanity was lucky that that tool that you have developed in biology was useful to be used for the pandemic or against pandemic. Isn't it true that we have to rethink the way how do we do research in biological sciences? And isn't in reality, because your approach, I mean the Flagship Ventures approach to research in biology, is different than what the others are doing. You are basically, from what I understand, are trying to jump quantumly in time ahead, see what is needed, then come back and try to say, okay, we definitely need this, now we have to try to find it. So there is a very important element of future prediction, which is the same with physics, but you do that based on formula. And this is based on completely different modeling of it.
Yeah. So I agree with what the premise of that you're laying out. So first, I'd say it's important to understand in biology that what we experience, the cells that make us up, and what we experience all over nature, are the result of a Darwinian evolutionary process, which is essentially variation, selection, iteration, and is highly dependent on the path that has come before it. In other words, what exists is a function of what existed before, over millennia and millions of years. And as a result, the system is dynamically, constantly adapting and trying to survive and gain advantage. And so a formula that would essentially model Darwinian evolution would be needed, which does not exist, in order to even backwards explain what we're observing. And keep in mind, historically, we don't have the intermediate steps as artifacts that we can actually point to. So it's difficult to and by the way, if you started the same experiment in the beginning of when the first biological molecules would have assembled and formed the form of a cell, you would end up in a different place than we are today if you ran it a second, third, fifth time, because it's a complete product of the intermediate circumstantial little fights that happened to compete and win in the survival of the fittest idea. That is not fully understood by people, especially physicists who've looked at the space. People like Schrödinger, who wrote this famous book a long time ago, What is Life? And he attempted some physics musings in the biology field. Was quite remarkable the way he thought about it, because he was trying to find the essence. But even in his manifesto, the degree to which evolution governs what we experience that's not a comfortable thought to kind of the reductionist kind of physics mentality. So that's an important thing in my view. Will we come someday to be able to actually develop a simulation of life that could at least explain some aspects of it? We are working on that, and I think some of the new AI tools give us the expectation that it might be possible in limited ways. You can do laboratory experiments in evolution and at least begin to mimic those. So that's one thing I'll say. More broadly, you have to understand kind of what is the challenge in biology is that you have cells, which are kind of the, I'd say, minimal reducible unit that can perform an energetic function and an information function that is really what's happening. That cell comprises tens of thousands of different parts that interact among each other in potentially hundreds of different ways. And that's one cell. And there's trillions of cells inside our body. One cell is at a level of complexity that, in any case, humans are not adept to be able to explain, because we can keep 10, 15, 20 things straight in our head. How are we supposed to offer an explanation of thousands of things interacting in hundreds of ways? And I'm simplifying, the numbers might be. So I think one of the problems is humans and our way of using language to communicate information, however profound our mechanistic understanding is, actually fail when it comes to this system, because nature has not simplified itself in the form of biology to essential tenets such that humans could communicate them, if you know what I'm saying. So instead, I think what you need to do is you look at the current environment we're in, the measurement techniques we have are actually increasingly sensitive, powerful, and we can generate millions and billions of data points on any given cell now, which we do. And then the question becomes, can you, by looking at enough instances, enough perturbations, develop a model, generally these days it'll be based on machine learning techniques, that can at least describe what you've observed and begin to say what you might observe if you do further perturbations. And that type of model actually has a big advantage and a big disadvantage. The advantage is it will help us navigate this complexity. The big disadvantage is that it belittles human beings, because humans don't understand how the model works and humans don't understand how life works. And so other than the human, it's just fine because the model is beginning to pick up what life is doing, but humans are uncomfortable with that because they lose agency. You cannot publish a paper saying, I understand what this mechanism of kidney disease is, when in fact you don't, but you have a system that actually can pretty much reproduce it. That's what the future of biological science will be, and we're right at that cusp. And so I believe that with tools, human-made tools, which humans should take credit for anyway, we will be able to do more and more with biology. But you're right, it will be totally different in mindset. And that's why I worry a little that in the US, for example, the amount of money that has gone in since World War II in physics-based research and some of the fundamental materials we've developed is nowhere near, in terms of it's much, much bigger than what we've actually done in doing the same biology. And so I'm hoping in this century, especially post-pandemic, that will begin to grow.
Yeah, I think it's fascinating, the theme that we are talking together, because from your description, and I was listening to you also yesterday at the Royal Society, I think it's fascinating that the whole the process of evolution is not happening just on the level of a body or individual or human. It's happening on the level of a cell. And as far from what I understood from our discussions yesterday, it's happening even on the level of a DNA. And not only the DNA as it is, as a big body, but specific parts of a DNA are also going through a specific sort of evolutionary process. Right. And they have not one way of developing themselves, but many ways. And that's where the DNA gets also into mutation, if I understood it right. So the complexity is very, very, very deep. It goes up to the individual parts of the DNA. And in order to have a sort of a physical or mathematical solution to that, we have to go to absolutely the basic elements of that and start describing it quantum mechanically, coming up, which in fact it's impossible. I mean, from the point of view of human brain and how do we see it. But as you said, the good news is that now we have a tool that can help us to do the modeling of this very, very complex matter, which is machine learning or artificial intelligence.
But I'll just give you one example. If you went the other way, physics would be like biology. If any given atom's history from the beginning of time was important to figure out what it will do next.
Exactly.
That is an assumption we make in physics that is not the case.
Yeah.
When you study black holes, when you study other kind of macro phenomenon, the history matters. But in any given formula, it doesn't say footnote, except if it's ever seen this, it's ever gone through. There's no history that you need to explain the phenomenon. Whereas in biology, actually, without the history, it's very hard to describe the phenomenon. At the trivial level of a single protein, you can if you isolate it, but you put it into a cell and the context is everything.
Yeah, but I agree with you. Of course, there is an evolution of the same elementary particles at the beginning of the universe or during the early times when the elementary particles and everything was created. But more or less it's a speculation in even theoretical physics. And we presume that if the conditions are more or less not very, 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 very harsh, elementary particles here on the Earth or in a galaxy that is 1 billion light years away from us is the same. We presume it's the same as as you were saying, while in biology it changes elementary particles. But the key is, again, to find a universal solution to many things. And I'm so happy that you referred to Schrödinger, because that's one of the books that I really like, because this is not about physics, it's about philosophy of life and the way we understand. And it helped me when I was young to understand that at the end of the day, we live in a unified universe. Whatever we do, be that in physics or in biology, it's more or less the same. It's run by the same rules of laws of nature. And it took me also to believe that even our social behavior is very natural. Mm-hmm. I think we are social. It depends, do we see that or not? And in many cases, it depends on the amount of the material that you have. Because biological bodies are very complex and interesting because it's big and very complex. The moment you have a society of 5 people, each of them, it's more or less individual elementary particle. But the moment you have 1 million people or 100 million people living together, right, it becomes a statistical body, and the behavior of people, amazingly, you can try to describe that through some laws of nature. I tried that. In fact, I tried for years, and my next book, which is coming, is called Quantum World and Quantum Politics. Mm-hmm. And it's all about that the world has changed. The way the world that we live now, it has changed because 100 years ago, we discovered the fundamental laws of physics or nature called quantum mechanics. It has created everything, started from satellites, our handsets, virtual world, and everything. But I have the feeling as well, and this is a question to you, that we are living through another crossroad of science. More than 100 years, there was a crossroad that people had to make a decision and do a phase transition from classical mechanics to quantum mechanics. I have the feeling that we're living an age when we're living on the crossroad where we have to make a jump. And that jump will be in biological sciences. Yeah. Why? Because the information accumulated that we cannot explain is huge. Why? Because we have a lot of tools that can help us to fix or to register the changes. And why? Because now we have a tool, a scientific tool that didn't exist before, which is artificial intelligence. Right. Then approach will be different, not a formula, but as you were describing, a model. Artificial intelligence helps us to make the model predict things, but that will open doors to phenomenal discoveries. Am I right or wrong?
No, I think that's what you describe is what we're doing in a pretty large scale, and a lot of our companies are predicated on that. I'll add to that the added element we haven't talked about, which is that we've known all along that biology is an information processing system. It stores, it transmits, it varies information. But because information theory, information science also didn't exist more than 100 years ago, and because the elemental structure of DNA and how it's transmitting information and the way translation and making proteins happens, all of that has been kind of uncovered in the last 50 years. We never really viewed this field as an information field. Now, it's increasingly the case that we're beginning to look at it as simply a code, right? When the genome sequences first started coming out, people used to call it a code for life, but it was a metaphoric code. It was not an actual code. Well, now it's an actual code, and the reason I say that is, for example, if you look at what we did with mRNA, mRNA was designed to be a piece of software that if you literally loaded it into cells, the computer of the cell would be able to process that and carry out instructions. That is programming a cell. That is programmable medicines. We call it the field that's emerging, programmable medicines. So before, medicines were small molecules and proteins that would have to go into the sea of heterogeneous compounds and find the target and touch it and then do something magical and cure a disease or treat a disease. The odds of that are pretty damn low, which is why we have so few drugs that work. But if you can put in a message, a code, and you can get the desired effect, then you can change the code, get another effect, change the code, get another effect. Those kinds of technologies, mRNA is one of them. There's a technology of tRNA, which is another type of molecule called transfer RNA we're working on. We're using DNA to do gene writing, which is to insert entire genes into genomes very precisely. So I think we're going to enter an era, and then of course with proteins, we've got a platform where we've, using AI, trained a system to be able to tell it what protein function you want, and it will give you an underlying DNA sequence that will do that. Not one, but thousands. Well, you might say, well, that must be a physics problem, because as you know, especially here in the UK, DeepMind created Google's DeepMind created a program called AlphaFold that they've made available, and it can predict three-dimensional folding structures of proteins. In our system knows nothing about what a protein is. It knows nothing about what an amino acid is. It knows nothing about what folding is. It just literally creates correspondence between a function and an underlying DNA. And when we started doing this 5 years ago, people said, well, how do you know that proteins can be represented through a DNA sequence? And of course, the simple answer to that is, last I checked, that's the only thing that gets transmitted generationally is a sequence of DNA. Mm-hmm. If the DNA itself did not know what protein to become and how to fold and how to do all this, we wouldn't work. There's no instruction manual so in a way, all the sophisticated things we've done to try to figure out how a piece of DNA becomes a three-dimensional protein are all innately part of that same code. So what we said is, maybe we can abstract the middle and just create correspondence between function, and we're doing that. So now you can, if another virus shows up and there's a piece of the spike protein of the one that's become now very famous that you want to direct an antibody to, you can sit in front of a computer, say this part, and then without knowing anything about anything else, we can specify an antibody, make it, test it in the lab, and it'll bind there. We've shown that. And we just published it in Nature a month ago, our whole code. Nobody ever had seen that before. And in fact, yesterday, Nature had that as its second most kind of popular, cited, etc., or at least attention-grabbing article in Nature this year. Why? Because we went a step further than what the three-dimensional folding does. So why I say all that is the programmability of biology, which is an innate feature, otherwise we wouldn't work, because that's all that happens when you transmit, is an interesting breakthrough in coming up with a new generation of tools that you might not understand the operating system exactly, but you can co-opt it to do what you want.
But philosophically, it's I think the philosophical part of this wonderful discovery or discoveries is that we live in one world, and everything what is happening here is basically run by the same nature, same rules, same laws, and same behavior. And it's fascinating that you can do so deep biological research and get so deep biological results just basing your research on an idea of simple coding or mathematics or mathematical modeling without, as you said, forgetting about what is there, what matters is what sort of information goes and how it controls. And in many cases, it's more or less the same when you speak about non-live materials as well. So we are coming a bit closer, but probably that issue is far, far ahead, to address something that people were always fascinated, the unified theory, which is in physics, but how do you unify four forces, which is the gravitation, electromagnetic, weak and strong. But the challenge is not that. I think the challenge will be the grand unifying theory, which put together not only these four forces of nature, together with something that unifies it with other objects of this universe, which are biological objects or social objects. And I think that the fact that they are all governed with from the same evolutionary behavior, because we can try to do the other way around, to that development of evolution of cosmos, basing on some ideas from Darwinian evolutionary theory, because, or our societies, how we are developing, how people's societies, that each of us were becoming more and more virtual as a particle, and we don't care about what we do here and there, but because we are a data. managing social amounts, numbers of people is becoming more and more. How do you manage specific data? Individual is a data. I mean, how much money you have, where you were born, what do you do, what are your capacities, interests, do you like this music, that? It's all data. And all together, how do you model this data together?
Mm-hmm.
But that brings me to another fundamental question, which is, there is a lot of talk about the importance of artificial intelligence, let's call it like with that name, and also threats that are coming from artificial intelligence. I'm not a biologist, but there are millions of people that do believe that even pandemics like COVID were man-made. So it was somewhere in a lab, there was an experiment which was not regulated properly or controlled, and this specific virus, which was just a result of a specific experiment, went out, and just we had the pandemic. So the question is, how much we have to be afraid of doing biological research in relative or compared with what we are doing in artificial intelligence? Should we be more afraid of artificial intelligence or unregulated biological research?
I mean, look, I think as is well known,
It's not a scientific question. It's just about.
I think as is well known, any new science, any new technology can be put to good and bad use, and biology and chemistry and physics with atomic bombs and with many other things have been put to various uses. And I don't think this is any different in biology, and I don't think it'll be any difference in AI. I mean, I think AI is a new output of computer science that is basically gathering more and more human-like, at least information processing capabilities. And the reason it makes humans feel kind of uncomfortable is that it is actually emulating humans, and the way it presents answers to questions, the way it seemingly understands the question or the nature of it, all of those things are new to humans. And anytime something is new, people somehow get scared. If you think about it, the example you gave in biology, I mean, in nature, there are unseen, infinite number of experiments that are going on, creating new viruses all the time, and we're not
Naturally.
we're not regulating that. And so I've always found it a bit odd that we actually fear misuse of biological capabilities amidst a sea. It's like saying, if will a piece of water represent a threat? It could, but there's an ocean of water already, and it can actually do the same thing and more, and without any intent, just by this, whether a virus, a lot of the, for example, avian flu pandemics or some of the strains are clearly evolving in nature, so that people are not worrying about whether it's man-made or not. But sure enough, they are fatal, and many other diseases. So I think in biology we have to realize that experiment is far beyond our ability to regulate, and so we can affect what humans can do, but humans are doing a tiny fraction of what nature is doing. Instead, I'd much rather figure out how best to protect humans by understanding the immune system, which we don't really understand very well, by arming the immune system like we did with mRNA, and getting, like, for example, could we give 100 different mRNAs to somebody, not one, not two, not three, and protect ourselves against any number of threats, real or foreseen? Should we give them 1,000? Should we give them 50,000? I'm not suggesting it, but those are questions that, regardless of what the intention is, we can arm ourselves against and protect ourselves against.
From everything.
Yeah, it's almost like saying, okay, I want to regulate, people writing nasty computer viruses, as opposed to saying, no, actually, I want to protect my network from said viruses. I will assume people will make these viruses. So that's the way I think about biology in that regard. In AI, look, I go a long way back. When I was an undergraduate, that was the field that I initially was going to get into, and in fact, I did some work in this area back in the early 80s, mid 80s. And at the time, artificial intelligence was all about expert systems, symbolic logic, all these things that were being done to try to represent knowledge in ways that was computable. And from there, and it was being used for the same things: medical diagnostics, language translation, all that robotic kind. So people were doing these things, especially at MIT where I was. What came about recently is kind of more of an evolution, literally scientifically, of those capabilities, much more powerful. But I would say I view AI as two things. One is augmented intelligence, and the other is augmented imagination. So the generative AI, the most recent versions, whether it's in images or it's in words or any other form, it allows us to actually augment our imagination. It can actually do creative stuff. I tell people, for example, that what is viewed as a bug in ChatGPT, which is it hallucinates, is a feature when it comes to evolution. Because hallucination is just variation, and if you apply rounds of selection, you might come up with a beautiful poem because it was reiterating a poem incorrectly. That's where creativity comes from. So I actually view it all as, how do you augment the human endeavor? People worry, is it going to replace the human endeavor? And in some areas it will, summarizing documents, and there was like 1,000 things you could think about, taking notes in a medical meeting. I think that the humans who figure out how to use it as augmentation will forge different paths, and the people who view it as, like they do with immigrants, they're here to take our jobs. Now the immigrant is AI, it's here to take our jobs. I think that always existed in society, and it will. And I think it's all about education. The interesting question would be, not only how do you use AI in education, but how do you educate for a life with AI? And by the way, we've done that before. I mean, I was a high school student learning chemistry using slide rules before calculators were available, before computers were available, as you've gone through all those experiences. And each time everybody said, well, how do you train people for a life, or should we even train people for a life with computers? Some people said, of course you should train people for a life because that's inevitable. Other people said, yeah, what if I don't really need a computer for my job? What if I can do my job? So that same thing is playing out here. Give it 3, 4, 5 years, and the vast majority will assume. I learned a long time ago the expression that what's the difference between an innovation and an appliance when it comes to home, is that if you grew up with it, it's an appliance. If it enters your life when you're an adult, it's an innovation. Yeah. And whether it's dishwashers for my mother, right? Dishwashers and appliance to me. For my mother, it was like, wow, look at this. Some machines doing what my family used to do. These are things that I think we need to apply to AI as well.
Yeah, but in any case, we're living fascinating times.
No question.
And when I'm thinking about my personal life, I don't complain. I was born on a different planet called Soviet Union. Never could imagine that I will end up here. But one thing was, even back in Soviet Union, when you were in science and doing science, I had always this feeling of universality of science and knowledge and the nature itself. Like you, in 1985, I created, back in Soviet Union, in Armenia, the first department of mathematical modeling of complex systems. Of course, the computers that we had were mainframe computers, nowhere close to what we had today. And I came there from doing research on structures of celestial bodies like pulsars, bursters, neutron stars, modeling them. And there was then a fight, I think, what is the true science? If you don't describe a neutron star with a mathematical formula analytically, then this is not science. Because what you have is not analytical formula 1 or 2, but you have a sort of a model computation, and then the results that you get, how this body behaves, comes from a computer. It's more or less the same type of research that you are praising now to do in biology, but the battle was there. But I think what we have, and now I fully agree with you, we have seen all this thing about innovation and appliance, because computers were innovation. People were afraid that they will basically take over jobs from people, but in reality they create hundreds of millions of jobs worldwide. The same will happen with artificial intelligence.
No question.
So I think this is something that I would love to continue forever, these discussions, but there is one thing that we not learned at all to understand its feature, which is called time.
Yes.
We don't understand our immune system, but there is something beyond that which is much more philosophical today, which is called time, and time is not something that we can control. And I think, unfortunately, the time of this interview comes to an end, and I would like to thank you, Noubar, for this
Pleasure.
fascinating discussion, and I hope that we will have a couple of others, because one of the roles of someone like you, a scientist, entrepreneur, someone that is living a life of creative life, and one of the important things that you have to do is also spare some time for public education. Because as you said, it's all about how do we perceive things. So thank you very much again.
Thank you. My pleasure.